Silos. Okay. So we've got silo with a cylinder part and a hemisphere part at the top. Okay, so let's see. Metal dome 1.5 times as much. So we can call the cylinder cost K, and then what's the cost? So per, what is it? Per meter cubed. So this is going to be cost per meter squared. Right, okay. And then, so then what will this be? 1.5 K dollars per meter squared. Okay. The volume is to be 750 meters cubed. We want the dimensions that minimize the cost of materials. So, and then there's no floor, and then this is all open in here. Okay, so what's going to be the centerpiece of this problem? What's going to be the centerpiece of the problem? He wants a cost function. Agree with that? Yeah, because we want to minimize the cost. So if we want to use calculus, then we need a cost function. And we're going to use our rate of change where it pauses, or where that derivative is 0. So this cost function is going to just in general be cost of the cylinder plus cost of the dome, right? So that's going to be the overall structure of our cost function. Okay, so cost of the cylinder is going to be area of the cylinder times K, is that right? And this will be the area of the dome times 1.5K. Still doing okay? Is it right? Because this is our cost per unit area, and this is cost per unit area, so then we need to... So the area of the cylinder is essentially what shape? Yeah, but essentially what shape is that lateral tube? Not a circle. We want to find the area. What are we going to use to get the area of that cylinder? So if you imagine cutting it and then opening it up, what are you going to get? Rectangle, right? So that cylinder is virtually a rectangle. What is this dimension? We'll just call it h for now, okay? And then what will this be? Circumference of the cylinder, which is 2 pi r. So the area is 2 pi r h, okay, plus, what do we got for the surface here? How are we gonna get the surface of the dome part? Half of a sphere, right? So we need the surface area of a sphere, which is surface area of a sphere. So you just got to look that up if you don't remember. 4 pi r squared. So half of it will be 2 pi r squared times 1.5K. So now we can maybe think about what will be the most convenient variable. So we need one independent variable that will generate our cost. What do you want? So R, H, or K? It's not going to be K, because K is just the relative size of just the two different costs. So K is just going to stay K. So yeah, so let's do R, and then all we need to do is find what? H in terms of R, and then we'll be ready to go, and we'll be done practically. So we want C of R. So what is going to get us that H in terms of R? Right, the volume. Okay? So the volume of this thing is the total volume of the silo is 750 meters cubed. So this, the volume is going to be able to get us H in terms of R. So what would you say the volume was? Pi r squared times the height. Is that it? Right? And so that's that. But this volume that we have is the volume of the silo, right? If it's the volume of the silo, then that 750 isn't just the cylinder. What else do we have? Plus half. So the surface area of a sphere is 4 pi r squared. Volume of a sphere is 4/3. If you don't remember, it's just pi r cubed. You just look it up somewhere. But we would have half of that. So it'd be 2/3 pi r cubed. Okay, have I lost anyone yet? Everyone following along? Okay, what was our goal? So our V is 750 equals this thing. And we want to solve for? First step to solve for H. We're going to subtract half of the sphere volume. And that'll equal pi r squared H. Next step, divide by our pi r squared. So I think I'm ready to write the answer here. So 750 minus 2/3 pi r cubed all over pi r squared. Did I lose anybody? So the process really feels a lot the same as many of these. We just have some significant algebra that we're and geometry that we're working through. Okay? Any questions? So now this is our H, and it goes here, and we have this cost function as a function of R. So see if I can get it to fit, 2 pi r times 750 minus 2/3 pi r cubed all over pi r squared. We'll get some cancellations here, that's nice. K plus that. Which I think once we can do some simplification here, that'll be a very manageable derivative. So what can we simplify here? Pi goes. I got r squared here in the denominator and 1 r in the numerator. So it leaves us 1 in the denominator. All right, so then we've got basically 3 terms. This first part here gives us 2 terms, because 750 minus, and then this term here. So I'll simplify it one more time. Equals, I'll do it in black so it stands out. So it'll be 1500 over R right? 2 times 750 over R. And then for this second term, we've got R cubed in the numerator and R in the denominator, which leaves R squared. So we got minus 2 times 2/3 is 4/3 pi R squared. Check my math. Make sure you agree. So that becomes R squared. 2 times 2/3, 4/3 pi R squared. And those are both times K. So this is that's times K minus that whole thing times K. and then plus this, and we can do 2 times 1.5, which gives us 3. So 3 pi r squared k. And I think we're ready for the derivative. So, did I lose you? Did I make a mistake? Any comments or questions? That's our C of R. So this gives us the cost of the silo as a function of the radius that we pick for the silo. Agree? Some people are agreeing. Anybody have a question? Did I lose you? If I lost you, ask. Are we good? So, can I leave it to you from there? No, let's just do it. So, let's do, I'm going to rewrite it. If I rewrite it, I'm going to erase. Let's see. I'll just erase here. Make some room for calculus. Got all the geometry done? Okay, so how are we going to find the minimum cost? First derivative. Let's crank it out here. I think it's going to be negative 1500k over r squared. That's supposed to be okay. All right, can we combine these? They're both pi r squared k. So what's 3 minus 4 thirds? 1 and 2 thirds? Which is 5 thirds? Is that right? 5 thirds. Great. So we're really saying this is plus 5 thirds pi r squared k. Derivative is b plus 10 thirds. This is with respect to r, right? Pi r k. Agree with the math? Everybody good? All right, so to find potential location of minimum, 0. So we're going to set this equal to 0. And so we can bring this over to the other side and cross multiply, right? So we're going to add this to both sides, cross multiply. And I think, can I do this all at once? Or just multiply by r squared. So it's going to be 10 thirds pi r cubed k equals 1500k. So I added this over here, and I multiplied both sides by r squared. Is it fair? K's can go. And we are home free. R cubed is 1500 times 3 is 4500, 450 over pi. So I multiplied by 3, I divided by 10, and I divided by pi. Stop me if you think I made a mistake. Don't let me dig a hole. So r, we're thinking is the cube root of 450 over pi. Okay, how can we make sure that this is giving us a minimum cost, right? It could be a maximum or it could be something else. Second derivative, okay? So in the second derivative, what will that term be, positive or negative? This is like r to the minus 2, right? So when we take the derivative, negative 1500 times r to the minus 2, what will that be? Positive, right? What about this? What about this? Positive. And then we're going to plug in a positive value of r. Second derivative will be Positive. Does that confirm that we have a minimum? Second derivative positive means the rate of change is doing what? Increasing, right? This is second derivative positive. And right there at the bottom, first derivative is 0. Minimum, right? Minimum. If the rate is increasing and you have a moment where the accumulation pauses, or the first derivative is 0, it's minimum. Okay, so they want the dimensions. So we've got the radius. You can get an approximation for that. And then we can use the thing I erased. Your height, that ugly height equation. You plug the r into the height, and it will give you the corresponding height. And then how do we find, if you want to define the minimum cost, what would you do?
Whatever thing is.
What would you do to find the minimum cost? Yeah, you're going to just take that r. This is an r value, so it's the radius that provides the minimum cost. I'm drawing the cost function here. So you're going to take that, plug it back into the cost function. It'll provide the minimum cost. Okay. Any questions? Okay, so this is what we'll do. You can keep working on these 4 and turn them in Monday with the new 4, right? So keep working on these. And we'll do one more on Monday too. They're all different. They're all kind of the same, but they're all different, right? Every one is different relationships, and so we just got to practice lots of them. So hold on to this. Use it to study for your quiz.
We just have to know all of the basic sphere.
Basic ones. If it's something that's out of the ordinary, I'll give it to you because it's something you can always look up, right?
Right.
Yeah.
Okay.
So like area of a square, area of a circle, these kinds of things for sure you should know.
Okay.
But surface area of a sphere, I'd give you a surface area of a sphere,
Okay.
or volume of a cone, I'd give you that.
Okay.
Things like a little more complicated things. Other questions?
On this career response situation, like on this one, I drew it wrong. I don't know why I thought this, but I drew a hole, like it was inside of it.
Haven't you driven in the country yet? Silos, right? Silos. But anyway, go ahead.
But I drew it wrong. So
Okay.
if we draw the thing, you look at our drawing and see what we did, and we have partial credit.
Yeah, you get in
Sometimes
that
these
scenario.
These always confuse me when I read the problem. Like I don't always see it the same way.
So she's bringing up a really good point. You got to really make sure you understand the setup. You got to have a correct image of what's being described, because if you don't, you're doing all this work that's just incorrect. So, however you can check that. If you want to send me an email, if you want to visit us in office hours, if you want to get on the net go to Google Silo and hit images, right? And then that would help. So any way you can assure yourself that you've got the correct image and the correct visualization of the situation, because you don't want to get into all this algebra if your setup is wrong, because it'll be all incorrect. Okay? So that's a very good point. Other questions? Okay, so in 4.3 you had a sketching exercise. We never really did that in class, so let's practice that. Can I erase? Okay, so if this was an accumulation function, could you sketch the rate function? If this was an accumulation, could you sketch the rate? We should be able to do that, so let's practice that. So how would you start? If you wanted to, this is an accumulation function, you want to sketch the derivative, or the rate of change of this, whatever is happening here. How would you start, Corey?
Well, to begin with, your accumulation is decreasing.
Okay.
And so the rate is negative in that case. So you're going to be starting at a negative point.
Okay, so he's looking. Are you looking at this part of the graph?
Yes, sir.
So looking at this part of the graph, he says that the rate of change should be negative through here. Okay, and where does that end? Is there some kind of critical or key point? Where at? Here?
Right there. No,
Here?
no,
Here?
yeah.
Here's where it stops decreasing.
So all through there, you're saying that the rate should be negative. And when we're graphing the rate and it's negative, what does that mean for our graph of the rate? Is it flickering? What's happening? Stop. Okay. What does that mean for the graph of the rate if the what's that? Passes through zero?
It's going to be positive right there.
No, I'm talking about this part here. So I'm talking about to the left of this point. So Corey and Nigel are saying? Below the x-axis. Okay, what about right here? Pass through the x-axis. So the accumulation is doing what right here? Rate of change is? If your accumulation pauses, then your rate of change is? Zero. It's not changing, right? For a moment, it's not changing. So the rate of change is zero. Okay, so you're saying that to the left of this point, our rate of change is below. So what is the rate of change doing from here to here? Is it increasing or decreasing? Increasing or decreasing rate? So is it here's the key to answer that. Is it becoming more or less positive or negative?
Less negative.
One more time?
Less negative.
Less negative and more positive. The rate is becoming less negative. That's right. So this is an increasing rate of change because the rate's becoming less negative. So what will that look like over here?
Below the axis and come up to that zero.
It's going to have the least rate will be here, and it will be like this. Is that right? Okay. So somebody else. Okay. Do we agree with this? Okay. Great. Okay. So now, where would we go from here? So what would you look at, kind of in this next part of the graph, to make progress from here? What would you do? Talia.
So let's up until about 1, the rate of change is positive.
So from here to here, so to about 1, you're saying that the rate of change is positive. Okay. Okay. So it's positive, and where's it increasing to?
Up until like 0.4.
Okay, around 0.4, and then it's increasing and the rate is positive and decreasing. So the rate here is positive and increasing, and then positive and decreasing. How does that graph? So let's break that up into two parts. So let's say this root is where that rate changes. So what's it going to do from here to here? Increase? And then what's it going to do from here to here? Decrease.
Back to zero.
What will happen at this? What's our rate of change here? Zero there. It pauses, right? So now it's positive, but decreasing. Okay, now starting from here, what happens? Rate of change is negative. Is it decreasing or increasing? Is the rate increasing or decreasing? More negative, therefore decreasing. Decreasing rate. And it's a negative rate. So negative rate means it's below, and it gets more negative, right? Questions on that? Okay, now I'm going to leave that up. Now, let's pretend the purple one is the rate of change, and we want to sketch the accumulation. And to just really, we'll leave this in as a distraction. Okay, I'm not going to erase it. We'll leave it as a distraction. See if you can do it. So, purple one is now rate of change, and we want to sketch accumulation. Dan, how are we going to start?
I would start the same way, break it up.
Break it up, okay.
And it looks like the first part, it's the rate of change is becoming less negative. It's negative, but it's becoming less negative.
The first part over here.
Yeah, from yeah,
So, what's the rate of change here?
negative.
Is the rate of change negative?
Or I'm sorry, positive. Yeah,
Why is it positive?
because it's getting less negative.
It's above the x-axis.
No, it's just because it's above the x-axis, right? So this is all positive rate of change.
I see.
Zero.
And what about right there?
Pauses.
0 rate of change. And through here? Negative rate of change. So we have positive rate of change, and then 0 rate of change, and then negative rate of change. What scenario is that? So positive rate of change means the accumulation is increasing. 0 rate of change, and then now negative rate of change means the accumulation is? What scenario do we have? That's maximum. You see, this is maximum. So I'm just gonna pick a place for that maximum. I'll pick a place like right here, okay? Because we know there could be many accumulation functions that have this rate. So this will just be the one. So to the left of this point, what should I draw? Increasing, right? Because this is positive rate and getting less positive, right? And that's shown here. Positive rate getting less positive. Okay? And then decrease. Okay? The rate is decreasing. And the rate is getting more or less negative. More negative. What is our accumulation going to do through here? The accumulation is decreasing, but the rate's becoming more positive. And so let's look at this. So we're decreasing, and then rate of change is 0, and then rate of change is? Rate of change is negative, rate of change is 0, rate of change is positive. What's our scenario there? This is minimum, right? Rate of change negative means decrease. Rate of change 0 means a pause. Rate of change positive. This is a minimum situation. So maybe here. Did I lose you? So this is negative rate. So our accumulation is decreasing, but it's becoming less negative. So what's the shape?
Concave up.
Concave up. All right, how about from here to here? This is our rate of change. It's positive and increasing, which means the accumulation is? Okay. What about this part right here? This is the rate. Is the rate positive or negative? Positive, therefore accumulation is? Increasing. But the rate is getting less positive. So the rate is positive, so the accumulation is increasing, but it's getting less positive. So how is it increasing? Draw it with your finger. What do we have there? Max, because rate is positive, rate is 0, rate is nice. Okay, any questions on that? It's a really good exercise because it really forces you to know all those relationships between rate of change and accumulation, positive, negative, increasing, decreasing. So you can just, these are, just draw a graph And practice, right? Just draw any graph and say, okay, this is a rate of change graph, then try to draw the accumulation. And then draw another graph and say, this is accumulation, try to draw the rate of change.
I was gonna ask, do I have time to do like one more?
No. So that's what I say. So like after class, just make up your own. Just make one, make a nice smooth hilly curve that goes to the axis, and then practice. Okay. Questions about what we did? All right, good. Okay, so we're gonna we've been really focusing on the closed form rate of change function. So we did all those mastery rules. We learned all those rules for the mastery, which was given an accumulation function, find the rate of change in closed form, right? We had all the tricks and techniques. And then we've been using them, right? We've been using them, like, for instance, for the optimization problems. But, so that, this is kind of a whole section of the course where we focus on the rate of change from accumulation. So now in the remaining part of the course, we want to kind of step back and look at the big picture again, okay? Because we're still heading towards this kind of pinnacle idea of the whole course. So I want you to take a look at this. This should look familiar from maybe a month or so ago. And just talk with the person next to you and come up with as much as you remember about what's going on here, okay? So just to reorient your thinking, just come up with as much as you can about what you're seeing in this illustration. Go. Water.
So then like basically
But she put it out there. She put it out there.
A little lines this way, that's what I got.
She's got going for her.
oh my god.
Like, one thing too. Because she's
No, what do we know about them? So these horizontal things, what they are on that value is the slope on this value. So that one's at like, this is what you do, so that the slope of it over there, or the rate is 0.2.
Okay, so how about Andrew? Just tell me one thing about what you're seeing here. Just one thing. He said the blue function is exact rate of change.
Yeah.
Agree with that? I can do even better. Okay? So, in fact, it's the rate of change of weight as a function of time if we're dumping sand onto a scale. Okay? So it's the rate of change of the weight measured by the scale as a function of time. Adelaide, tell me something else. One thing.
The red steps are the approximate rate of change.
Okay? So over here, purple maybe, pink. The steps are the approximate rate of change. Agree?
Yes.
Cool. All right. How about Autumn? Tell me one thing. So tell me something else.
Using that information, because the step is the delta x, so using that information we could do an estimated approximation function on the right.
Estimated.
Accumulation.
Right.
sorry.
Okay. That's good. All right. And what is delta x?
Right now it's 1.5, but if you make it smaller, then you have a better.
Okay. So she's talking about delta x. We're saying it's 0.5, and she said this is an approximating accumulation function. Okay. Sharon, can you tell me something else?
For each interval, which is the delta x, the rate of change is constant.
Okay. In each interval, The approximating rate of change is constant.
And then the rate of change for each interval is the slope for the interval.
She said the rate of change for each interval then is the slope of our accumulation graph. Agree with that? Nice. Okay, good. Anything else to add so far? Okay, so when we were looking at this, I asked a question. I said, how can the accumulated weight, well, let's see. How can the accumulated weight between 1 and 2 seconds elapsed be calculated using the left-hand graph and the right-hand graph? So this was a question that we asked, very important question, and so you can work on that again. So how can so starting at 1 second and ending at 2 seconds elapsed, so from here to here, how could we use this version of the situation to calculate the accumulated weight of sand, and how could we use this over here to find the accumulated weight of the sand? Go.
So that combines those vibes.
And then on the other one, when you add one, like between 1 and 2, find the.
I think it's just. Yeah. So
Just like subtract the y value at 1, the y value is like left x.
Okay, did we come up with something? So, DJ, take your pick. He wants the right. He's going to tell us how we can use the right-hand graph to get the accumulated weight between 1 and 2 seconds elapsed.
So, can we use graphic calculator? Or can we use it as like, because if I was using this as graphing calculator, I would say, let's say our right one's a of x.
Excellent. So he's saying this is the accumulation function ax. Awesome. Okay.
So then I'd do a of 2
A of 2
minus a of 1.
minus a of 1. And can you explain your reasoning? Why? What is that? Why?
So a of 2 is asking for the total accumulation at 2 seconds on
Okay.
the graph.
All right.
And then we're subtracting it from the total accumulation at 1 second on the graph.
So a of 1 is the total accumulation up to 1 second.
Right.
And how is that represented? How is that total accumulation represented at 1 second?
black line.
Dot.
What about the black line, or what about the dot? How is the accumulation at 1 second represented? Beth? Yeah. She said the y value corresponding with 1. All right? Yeah, it's the output of this function. The output is, so a of 1 will output the accumulation up to 1 second, and that's our y-coordinate, right? Y-coordinate. And so we take a of 1, we get the accumulation. That y-coordinate is the accumulation up to 1. And then so a of 2 will be total accumulation up to 2. So then y subtract. Lauren? Yeah, so we want the accumulation up to 2, but from 0? From 1. So we're going to subtract that off. Subtract off that accumulation from 1, and that leaves just the accumulation from 1 to 2. Are we good? Okay? How about the left-hand graph? Autumn, want to try that?
So you would look at basically the rate of change for like at 1 second. That's
This
that
one?
value would
Okay.
be the K basically.
All right, let's call it R. How about R3?
Okay.
Because this is R1, R2, R3. Okay.
Okay. And then at 1.5 seconds, that K value would be like R4.
Good.
And then you'd multiply those values, the Y value, by the change in X. So it'd be like 0.5 for each one, and then you would add those values together.
Give me the whole expression.
It would be R3 delta X. I guess you could, well, I don't know if I want to say 0.5 or
Yeah, either way.
plus R4 delta X.
This is what she's offering up. Agree? So little bits of accumulation are calculated by little changes in X. So these are like little delta Y's, right? And delta Y equals, for a constant rate of change, delta Y equals K delta X. And so every time we have a constant rate of change, we can use that rate to get that little bit of accumulation. Okay, are we good? All right, so now, same question. Same question. So now I've just changed delta x to be tiny. Turn this off. I've got delta x set now at 0.0275. Same question. How can I use both graphs to get the accumulated weight from 1 to 2? Same way.
You just have more differing rates on the left.
So she's saying there's more differing rates here.
Or 10 plus 1 plus 12.
So they only told me more.
Yeah, it's the same process. It's just there's a lot more rates.
Okay.
Sure.
So what will this look like?
Very long.
What's that, Tyler?
R12 delta x all the way through R56 delta x.
Whatever it is. Okay, so there'll be a lot more of these. Okay, what about this side? What about using it this side? Same, right? Same, okay. Okay, 0.0125. In fact, I'm going to turn off the actual rate and just leave the approximating rate function. So now I'm just showing the approximating rate function, and now we got delta x is 0.0125. Want to do it? Okay, how about if delta x is
It's a little easier now.
So I want you to write it out. Write out what for delta x of this.
No.
Right, yeah. Yes, I do. Someone's going to be able to do it. Someone can do it. So if you think you can do it, write out the accumulated weight from 1 to 2 if delta x is this.
What is that?
3, 6, 9.
Someone's smart. Someone's learned something. Who can do it?
Oh,
You've got 1 minute.
You want the city.
Everyone try to do it. So what's the accumulated weight from 1 to 2 if delta x is this blue number right here? Who has learned something?
Still 8.
You think you got it? No, I want everyone to think about it. Do you think you got it? What's that? Okay. Let's let people think about it. So, what I'm saying here is delta x is sufficiently small. Small enough that it doesn't make a difference anymore. What's the accumulated weight from 1 to 2? Using the left-hand idea. Okay. Who thinks they have it? Sharon. Integral. 1 to 2. What do you think? Is that what that is? So, remember doing that? We said when x is sufficiently small, our accumulation, we have this shorthand notation. Okay? And so what does that equal? So, what is it? A
Of
2 minus A of 1. Okay, so now I want you to write out the same expression. If we start at any value c, and we want to accumulate, starting at any value c, accumulating to any value. So this is a fixed value. We're going to start at c, but then we're going to let that where we accumulate to vary. Okay, so it's still a function. We're going to start, we used to call this a, right? So now we'll call it c, okay? So we'll call it c, starting at c, accumulating up to x. What would our accumulated weight function be now? So it's a weight function for accumulated weight starting at c to any value x. Let's see. Christina, what would it be? Yeah, so now rather than going from 1 to 2, we're going to just start at any fixed value c that we're going to pick, and then let x vary in terms of how far we accumulate to. So how can we express the accumulated weight from c to x? Now we got to be careful. Remember this? We need something different, because x now represents out here, and we need to think about accumulating bit by bit, so we need a different parameter t equals. Okay, so this is what we're going to be talking about on Monday. Very, very, very important principle right here. Okay, so you got your quiz today, and then you got 4 more optimization, and we'll pick up this discussion Monday. Have a great weekend.